Okay, ready? So here's the book. If you look at the back of the book, you look on chapter if you look at chapter back here, this section, you'll see is that these chapters all talk about hypothesis testing and data analysis and things like that. So basically the things that we went over last week. It goes into more detail than I did. So what I want you to do is I want you to sort of be able to understand the basics of statistical testing. I won't on the exam. I'm not going to ask you to do a statistical test on the exam, but you should know the basics of it. Good. Okay, and that there are chapters. Let's see. There's chapters 18, which does probability and confidence. So that shows all those distributions. Then there's hypothesis testing, chapter 19. And then chapter 20 gets into data, effect size, and interpretation of evidence. So I'll go over a little bit of that. I won't go over effect size, but I'll go over a little bit of kind of just how you interpret this type of statistics. So if you recall, on that we drew this and said that we had a mean of what, 36.5 or something, and down to 22.3, and then we said that if the area in these two tails was less than p less than 0.05, right? Less than 0.05, is that then do you reject the null or accept the null? Well, first, what's the null? For these two things, what's the null hypothesis? Remember, this is the standard care. This is the Manuka honey. So what's the null hypothesis? Say louder.
There's no difference.
Yeah, so the way you would write it, you say that there is no difference between what? What does this thing represent? This 22.3 and the 36.5. It's the days to heal, right? So there's no difference between the average days to heal between Manuka honey and standard care. No difference between the time to heal between Manuka honey and standard care. That's your null hypothesis. So if it looks like this, do you reject the null hypothesis or accept the null hypothesis? Let me say reject. I'm going to say, show me either accept. No, I guess you should do it the other way. Accept or reject. So show me either accept or reject. That's right, reject, right? You reject the null hypothesis and you conclude that the means from different distributions. That's what it's saying. So it's saying is that you're going to reject this in favor of one that says that this thing comes from a distribution that looks like that. Following that? So that's the basics of hypothesis testing. This is called a two-tailed test. Why do you think it's called a two-tailed test? It has two tails. Because there's 0.025 in this and 0.025 in this. So you add those two things together. If you only have it like this, so there's 0.05 here in this area, and it's called a one-tailed test. So you'll see this language, they'll talk about two-tailed test or one-tailed test. I don't think I've ever seen a one-tailed test in a published article. Everything is a two-tailed test. Why? Just because it's a tougher test, right? Even though you sort of think your hypothesis is that this thing is going to be significantly less than the number of the time to heal days is going to be significantly less than the standard of care. And even so, if you got a number like 30 or 42.5 way up here, you would think, oh, not good, right? I'm surely going to accept the null hypothesis, but but practically you could also reject the null hypothesis to get something up here, and then you would say, oh well, my null hypothesis that there's no difference is rejected in favor of the one that this is Manuka honey causes longer time to heal. Good. Okay, so if you look at this. So this is the paper that we went through that first day, where it shows odds ratios. So the odds ratio there is, well, let me go down to odds ratio. There we go. So this is adjusted odds ratio, AOR, and you'll see that it has a number like 1, and then it has a lower bound and upper bound of this. Well, what this thing is testing is it's testing that, is the ACE count of 1 equal to the ACE count of 0. Right? So your null hypothesis is that you're no more likely to go to a GP if you have an ACE count of 1 than if you have an ACE count of 0. That's your null hypothesis. And so the way it tests it, and when you put it in odds ratio terms, what this means is that they do it in terms of like saying probabilities. So it's really saying, is the probability of going or given as a hypothesis. The probability of going to the GP if we have an ACE score of 1 is the same as the probability if you have an ACE score of 0. That's your null hypothesis. So you're seeing if you're going to accept or reject this null hypothesis. When they do the odds ratio, what they're doing is that rather than sort of doing it to 0, is that they do it in probabilities. So if the probability is equal to 1, then there's no difference between the groups. If the probability is less than 1, then the thing is less likely. If it's greater than 1, then it's more likely. And the way that you interpret the coefficient, in this case, that 0.13 is that means it's 13% higher than going with 0. But the testing part of it is still the same. What you're doing is you're testing to see, is this thing different? And then an odds ratio just puts it in terms of these probabilities like that, but it's the same basic test. And so in this case, what it does is that you see it has a lower bound and upper bound for the confidence intervals. So what that means is that it's testing this, where this thing is 1, and your lower bound is what, 0.92, and your upper bound is 1.38, and this number is 1.13 in there. So that's what you're testing. In this case, do you reject or accept the null hypothesis? Do you reject or accept? 50-50 shot, getting it right. How many say accept? How many say reject? The answer is you accept the null hypothesis, that there's no difference. I mean, I know it's backwards logic, right? Because you accept that there's no difference, but that's the way that, what you're doing is you're setting up this tough test. And so you're rejecting the null hypothesis that these things are different in favor of the one that says that they are different, that they're from the same distribution. Now, if you look at the next one down, this one here, That one is based, it says that, okay, so now we've got the same kind of, same thing. The distribution around one. What's my lower bound? 1.21. What's my upper bound? 1.83. What's the number? 1.49. Right. That's not right. I think they made a mistake in that. Because the upper bound. Oh, upper P, okay. Upper P, why was the P? Because it should be, it's like your 95% confidence interval should give you the balance. In this case, though, they're saying that it's 1.49, but I'm saying it's significantly different. So I mean, because it has to be less than 0.001. Rudy, you took epi. Do you know why it is that the confidence intervals, I mean, that it lies within the confidence intervals, yet they're saying that it's not significant? I mean, that is significant.
I'm sorry, I could barely hear your question. What about the CIs?
Well, look at, here's the question. This is 1.49, right?
Mhm.
Oh, I see why. Oh, never mind. I see what they're doing. My mistake. They're doing it this, they're showing you not where, yeah. They're showing you like this. 1.49, like this. So they're saying that this is the distribution that it's coming from. And so one then is down here. Right? So it means that, you know, again, this is it's testing basic or showing you that, well, here's the mean, you know, here's the number, the 1.49. So that would be the center of the distribution. And so then, you know, here's your 95% confidence intervals for that distribution. And you look to see, does one lie within that confidence interval? So the answer is no, one doesn't lie within that confidence interval. So that's why they say in this case, you reject the null, because one doesn't lie in. I mean, so, because they could do it either way. They could either do it where that they show again this thing, you know, if this was they could show it this way, where one, and you have your points here, and then you have 1.49 way out here. Or they could show this like that, and then C is one line. So they're showing it this way. So it just means that if one doesn't lie within there, then it's significantly different. It's like this one. You can see this one that the score is 2.34. And that the confidence intervals for that is, so you have 2.34 like this. And then you have a lower bound of 1 point something. 1.88. And if that next down is 2.92. So it looks like this. So one is way down here. So this one is therefore rejector. So rejector. So rejector. Right. So this one's also rejected. So basically the way to read these things is that if one does not lie within there, then you reject the hypothesis and assume that they're different. Different means that this is a significant prediction. You know, because your null hypothesis is that people who have, in this case, 3 or more than 4 ACEs scores are no more likely to use the GP than people who have 0 ACEs score. And you would reject that in favor of the alternative, which is that people with 4 are more likely to use the GP than people with 0 score. Yeah.
Just to clarify, I'm kind of unsure. So is that value of 1 for like every graph, or is just specific one, something that it was?
If they show you an odds ratio, what you're always doing is looking to see, does one lie within that boundary? Does one lie within here? So does one lie within there? Yeah, so you accept the null. This is not significant, right? And that's what it shows there. P is not less than 0.05. P is equal to 0.242, right? Yeah. So what say it again?
Here for me, that is a significant. I didn't know you.
Okay, so what it's saying is that, see where that P, the P value of 0.242. It's saying is that if you were to have a distribution that looked like this, right? Is that, and here's 1.3, this area in here is 0.242, not 0.05, but 0.242. That's what it's saying. So it means that that's why you, in this case, you don't reject, because you only reject if this thing is P is less than 0.05. In this case, you know, they're giving me the numbers in there, so P is equal to 0.242. And let's say if it looked like this, if you had a distribution of like 1, and then you have on this end 1.25, and this one 0.75, and your value was, you know, 1.001, right? So you get that mean almost 1 for your odds ratio. Well, and now what you're doing is you're sort of, with your p-value would essentially be everything in here. So your p-value in this case is probably going to be equal to like 0.9. And what happens that as this thing gets further away, like 0.01, 0.05, then this p-value becomes like 0.75, and then it keeps going down until it gets outside of these bounds, and then your p-value is less than 0.5. It's also why, like in this case, they don't say p less than 0.05. They say p less than 0.0001, because it just means that, you know, it's so far out here, like here, that the number in the tails this way is so small that it's not even, they're not even going to give you the number. Okay. So summary. When you see an odds ratio, you look to see if 1 is in this type of mountain. If 1 is in there, then do you accept or reject? If 1 is in that bound, do you accept or reject? You accept. If 1 is outside that bound, then you reject, right? So that's how, and reject just means that it's a significant difference. All right, the other type of thing that you're likely to see a lot is t-tests. So this is basically a t-test here, right? A t-test is, that's just basically a t-test, is that. And so when you, you know, and the idea is that it's just the differences between the means, and then you use the standard deviations to figure out what the significant difference. But the other type of thing that you're likely to see a lot is something that looks like this. Let's see. So this is a paper. I'll show you this paper later on, just because it's kind of an interesting paper to read. Mass population screening for colorectal cancer. So I won't go through it right now, but what I'll show you is that when they get to the results, here we go. Logistic regression for test preferences. So what a regression is that, you know, if you think of a t-test as just comparing 2 different numbers and saying, is this number greater than that? That's a t-test. What a t-test between two sample means, I mean. But what you're more likely to see in these types of things are regression analysis. But regression analysis is based on, is like, let's say if you have your say your independent variable is this is time yield, right? And here's Manuka honey, and here's standard honey. So it looks like that. So if you plot time to yield up here, you get 22.3 like that. And if you plot time to yield here, you get 36.5. So if you plot it out, that's what it looks like. Well, if you draw a line between those two things, is that, you know, what you are really doing is you're looking to see, is the slope of this line equal to 0 or not? That's what you're looking at. You know, so a line, you know, a line, y is equal to A plus B times X is the line, where A is your intercept. And B is the slope of the line. So what you're really doing there is you're testing to see, is this slope equal to 0? So if the slope is equal to 0, then what's this line look like? You have a line where the slope equals 0, what's it mean? It's flat, right? So if you have a line where the slope is equal to 0, it looks like that. It's just a flat line. Well, here's Manuka honey. Here's standard tip. If they were both at 36.5 days, you would say, well, there's no difference between those two things. Right? But in regression land, and if you do it with a line like this, what you're really saying is that, well, the line is just flat between the two. So this becomes important. Like, let's say instead of looking at this, you want to go look and see, given that you identified that Manuka honey is a great thing, you think, well, maybe more Manuka honey is better than less Manuka honey. So what you do is that you have, in this case now, we have time healing up here. And here, you give them like a one ounce of Manuka honey. And then in this group, you give 10 ounces of Manuka honey. And this one, 20 ounces of Manuka honey. Right? So now you have 3 groups. And now you're going to go through and you look to see, are those things different? Well, what you do is you plot it. And let's say that this thing, the time healing here, 1 ounce was, was 40 days. And the time healing here was 20 days. And the time healing here was 5 days, like that, right? Let's see if it looks like this. Well, you plot these things together. And what you're doing, looking to see is that, well, is the slope of this line equal to 0? That's really what you're doing. You're looking to see, as you increase the amount, what happens to the time to heal? Does it go down or is it flat? Now, because it's data, and what you really get is you get that, and then you get this confidence interval that goes around it, right? And so what you're really testing is you're testing, does the data look like this, or does the data look like that? Flat. That's what you're testing when they do a regression analysis. We're testing to see, is this data, your null hypothesis is that the slope is equal to 0, and the alternative hypothesis is that the slope in this case is less than 0. It's a downward slope. So if you look at this here, they have, this is a regression analysis now. So what all these things are, these betas, those are all basically think of those as like the slope of the line. So in this case, beta is equal to 0.03. And then, is it significant? Well, they're giving basically your odds ratio again in this case, right? So 1.03. And so they're basically saying that no. So that's the way you do it with the regression results, is that if you see that they're giving you a coefficient like this, right? Then what you're looking at then is you're not looking at the probabilities, you're looking at, is that number equal to 0? And then the statistics test will tell you whether it's equal to 0. But it's the same idea. The null hypothesis is that for a regression analysis is that the beta is equal to 0. The alternative is that the beta is not equal to 0. And so, and if it's negative, that means that there's a relationship that looks like this. And if it's positive, if the beta is positive, then there's a relationship that looks like that. And what this is called, and this is called a dose response. Dose response. Dose response. This is called a dose response. When you have, like, the more you get, the sort of the better outcomes you get, that's called a dose response. You can also have things like this. You could have it look like time to heal. You have 1 ounce, 10 ounces, and 20 ounces. You can imagine a case where you get too much of the stuff, it starts to become bad. So it goes like this, it goes, here at 40 days. It goes here at 20 days, and it goes here at 5 days. So if you give 30, then it goes up to, back up to 40 days like that. So you can have something that looks like this, where you get, a certain, a response for a while, then it changes. So those happen a lot. And in those cases, what you either do is you either try to fit, rather than the line, you try to fit some curve that looks like this, or you break it up. And you first look, does this is equal to 0, and then you test is this one equal to 0. That's the basic idea. So it means though that as you're going through, you're either going to see, comparison between means, or you're going to see these types of beta coefficients, these types of things where they'll show it as a beta. And the idea there is that you're looking at the slope of this line and you're seeing whether it's equal to 0. Okay. Questions? Yeah. Sure. So if you see a coefficient, so if you see an odds ratio, right, then you know how to accept or reject the null based on that, right? If 1 is inside of that bound, you accept. If 1 is outside the bound they show, you reject. Right? Nod your head. So that's for just an odds ratio. But they show you with coefficients, and you'll know that they have a coefficient because they'll show betas. They'll like at the top of that column, it will say beta. What you're looking at in this case is that, is this thing equal to 0? Is it less than 0, or is it greater than 0? That's what it's testing. And so if you get a number like, beta is equal to 0.03, right? What they'll show is that they'll usually show like a little star next to it. And at the bottom of the graph, it will say P less than 0.05 for all the star variables. And so what they're telling you is that for those variables there with the star, it's significantly different than 0. So, that's the 90% of the articles you see where they give regression coefficients, they're going to show it like this. And so if you look at the bottom of these tables, I'll find them for example, but it will say like P less than 0.01 and P less than 0.001. So what they're doing is they're giving you, like they're showing that for this variable is significantly different than 0. And it shows you at this level of significance. Okay. All right. So to conclude then of what we were talking about in terms of scientific method. So now this is the basics for how science works, is that you get data and you come up with your research question, and then you come up with your null hypothesis, and then you look to see, is the data such that you could reject or accept the null hypothesis. And that when you write it up in a journal, like when you go through these articles, you write it up, that method section should tell you exactly what they did. So it should tell you how they went from some concept like, people who are, males are more likely to favor colorectal cancer screening than females. How they went from that to how they actually go through and measure and how they actually define what their variables are. That process of going from these vague concepts to something that is very, very specific is called operationalizing your variables, right? So when we talk about operationalize, that's where you actually go through and figure out exactly, come through with exactly what is being done. And what you, and if you go to the method section, you should be able to see exactly what they did. You should be able to not just see, you should be able to recreate. So a good method section should mean is that you can then do that same study yourself. In fact, if they use questionnaires, they usually don't put the questionnaires in the article anymore. But what they do is they say, either go online and they'll make the questionnaire available, or you write to the author and the author will send you the questionnaire. And it's ethically on the part of the author that if somebody asks for the questionnaire, you send the questionnaire. Okay, but the idea is that with that, then you should be able to replicate. And as we talked about last time, there are problems with replication because, you know, if you, it could be is that if you can't replicate something, it could be because it's just because, you know, they got the result, which was out here someplace. But the true distribution was such that, you know, they just got a fluky result, which happens. In fact, it would happen what percentage of the time? What percentage of the time might they get a fluky result, which said that their, you know, their hypothesis was, what's that? 1 out of 20, right? Because that's the p is less than 0.05. So you get a fluky result. That's one possibility. Another possibility is that the researcher, you know, I won't say lied, but manipulated data. It's a second possibility. Third possibility is that the people who were replicating it didn't do a very good job and screwed up things. And you don't really know. You know, all three of those are reasons why you can't, you know, you may not replicate. But the idea is that over time, people should be able to replicate what it is that you did. All right, second thing, scientific method only considers things that can be tested. So, you know, we talked about this idea that, you know, how can you test whether there's a God or not? And I think that I'm feeling confident in saying is that you can't come up with a test for whether there's a God or not. And I say that because scientists for hundreds and hundreds of years have tried to come up with tests for God and hasn't worked. Hasn't worked meaning is that any explanation, any test that you can come up with and give me an explanation for why there's a God, I can come up with an explanation for that based upon there not being a God, and vice versa. Any explanation that comes along that you says proves there's not a God, I can come up with an explanation that suggests it's still consistent with there being a God. So it's just not a testable hypothesis. Third one is just be clear what it is that you're doing when you're testing. Is that, you know, you're not discovering the truth. What you're discovering is your data consistent with your, you know, your research question? Does it support your research hypothesis, or does it support the null hypothesis? And the last thing is that, you know, just understand the limits of the scientific method. So, you know, there's one, you know, kind of one fact about science is that science tends to like things that are parsimonious, means they like consistent, simple solutions. So one thing that bugged Einstein and is that, as I understand physics, is that you have quantum physics, which explains things at kind of the very, very, you know, small level. And then you have astrophysics that explains things at the very, very big level, but there's not necessarily, they're not the same things. And so they're not the same kind of theories. And so there's, you know, there's been long of this kind of search for the grand unifying theory that would not say quantum physics explains all these small things, but astrophysics explains all these big things, but rather you'd have a theory that explained both the small things and big things. This is sort of why Einstein made the comment that, well, God does not play dice, because what he was referring to is that quantum mechanics or quantum physics is all based upon the idea of probabilities. And so it's like, well, wait a minute. You have something that predicts really well, but it's all based on probabilities. And then you have things like, you know, why does my pen fall? Which is based upon things that they can say, well, every time it's going to happen this way. Things are more unstable and not probabilistic. And I mean, it's not like your pen drops 9 times, but one time it's just going to float away. Instead, they have more, you know, more solid laws as opposed to more probabilistic ones. So why is it that scientists, why did Einstein want to have one theory rather than 2 theories? Right? Because the 2 theories work pretty well, right? Small things get explained pretty well with that, with quantum physics. Big things get explained pretty well with astrophysics. Why did Einstein want one thing? Because it's just this idea that, well, there should be one thing. So science tends to like simple or parsimonious. They want things that are consistent with what's been done in the past. So it means that if you go through and that you're doing some type of study, you know, part of the reason why people look at how it compares to previous results is because science is supposed to build upon each other. It's like you're supposed to read what the literature is, and then you're supposed to extend what the literature's done by coming up with something that's a new test or a new variant or some type of new way of understanding. But it's all built upon what's been done in the past. So that, yeah, and that they set it up as a tough test, right? This 1 out of 20 test is a tough one, because it means that if you come up with a new idea, it's got to be something which is really, really bears out in the data. Problem is that people can get stuck in different types of ways of thinking, that science can get stuck in different types of ways of thinking. And so this is called a paradigm. So what it says is that, well, we have these paradigms for how we see the world, and that the paradigm then kind of guides how we go through and that we come up with ideas. And what happens over time is that paradigm shift. So, good example is does the earth revolve around the sun, or does the sun revolve around the earth? Right. So this has been, the Greeks thought that the earth revolved around the sun. And then came, in the 2nd century, they started to, the dominant kind of view was that the sun revolves around the earth. And then Copernicus comes along and says, no, the earth revolves around the sun, right? Well, in between the 2nd century and Copernicus, there were a lot of people, scientists who were killed, or people who were killed because they came through and they said, no, the earth doesn't, it's not that the sun revolves around the earth, but instead the earth revolves around the sun. And they got killed. And they got killed because the Catholic Church, liked the idea, favored the paradigm that the sun revolves around the earth. Why did the Catholic Church, why was so adamant about the paradigm that the sun revolves around the earth? Well, because, God created the earth, right? Who did God create the earth for? Men. Sorry, not women, just men. Just men, right? And so therefore, and God created all the animals on the earth for man to use. And so therefore, everything revolves around humans, right? Around men, including the sky. And so why is it that the earth would just be one little thing going around a sun? Why wouldn't it be that everything revolves around us, right? as humans? So that was the paradigm. Did it explain things well? Yes, it did explain things well. If you start with the assumption that the earth is the center of the universe and everything revolves around it, things get explained pretty well. It explains why the sun comes up there and goes down there, and explains why stars go like this, and all those different things that kind of occur. It all makes sense. There are a couple of anomalies though, and so one of the anomalies is what happens to to Mars. So like if you look at planets go across the sky, most planets, they go like this, right, across the sky. So over time, if you just plot a planet, the planet goes like that. And so for most of them, that's true. But Mars does this. Mars goes like that, and then it makes a loop. And then it goes like that. And so the question was, well, why does Mars make this loop in the sky? If you plot it over the nights, why does Mars make this loop? Why doesn't Mars just go like that too? So one theory is that, well, that's what Mars does, that God created it so that Mars does a loop every once in a while. And then, and so, yeah, it's the way it is. The other theory was that, what people like Copernicus were saying is that, well, no, if you think about the Earth rotating and Mars rotating, and they're rotating at different speeds, and you're a point here, then it's going to look because. So both of the theories explain the data equally well. There's no way to look at the data and say, oh, this theory definitely does better than this one, because they both can explain it. The only kind of flip is that in the Earth-centered one, you've got to just accept that every once in a while Mars does a flip, that God created it so that Mars flips every once in a while. Right? And so, why was it finally overthrown? Well, in terms of went from being the Earth is the center to when Copernicus comes along and proposes that the sun is the center. Well, it's not that there was any type of new evidence that came along. That kind of came later, but there wasn't really that much new evidence. it was that this was at the start of the Renaissance. People were more kind of believing in science and the scientific method. And so it was parsimonious. It was a better, simpler solution. It was one that had, huge implications in terms of how people viewed themselves, right? But it was, science basically took it over. I mean, it started to accept it. And so that's a paradigm shift where both things explain the data very well, and something comes along and changes it. There's lots of other ones. I think the most dramatic recent one is basically eugenics, right? So back in the 1920s, the U.S. scientific community led the way in eugenics. If you go to some of these museums, like the Philadelphia Museum has heads of people, brains of people that they were left because they were obsessed with this idea of brain size being the size of intelligence, and that there were going to be all these different differences between blacks and whites and Southern Italians and Northern Italians and Greeks and all this kind of stuff to explain why it was that certain people were smarter than other people. And so, this was the dominant scientific paradigm that went on. And it kind of went on, and then what caused the paradigm shift to go away from it? And this is the 20s and 30s. What caused the paradigm shift? Well, World War II, right? Hitler arises, says, well, Jews are inferior people, kind of going with and took it to the extreme. And so after that, after World War II, suddenly eugenics is no longer seen as something which is like, well, every once in a while it will rise again. So every once in a while it comes up with something. But for the most part, it's a paradigm shift now. That paradigm is now gone. But it was really the dominant thing in the 1920s and 30s in terms of scientists. All right. So the point being is that if you come through and you think about different type of theories, is that it's going to be influenced by the way you see the world. And that's why science is not objective. Right? So science doesn't find facts, and it's not objective. Because no matter what you do, it's going to be determined by the way you see the world. And even if it could be that you have a theory, so you have something more formal, or it just could be that the way that you're just, the way you're thinking about things. But it's whatever way you see the world is going to dominate. And the problem is that, it's not like you can set up statistical tests to kind of get over these things. So for example, here's one theory: Manuka honey has certain properties, et cetera, et cetera. It helps you feel happy. It makes you heal faster. Here's the other one: Zorak, god of healing, enjoys sweet things. Zorak currently heals wounds by raining down invisible cosmic rays on the wound. Because Zorak favors sweet things, he will rain down more invisible cosmic rain if the treatment is sweet tasting. Is that consistent with the Manuka honey thing? Yeah, hard to disprove. I mean, I guess, like you could sort of find a different thing that heals better than Manuka honey that isn't sweet. But then I could just say, well, Zorak also likes peppers too. So if you're treating it with peppers, is that Zorak also likes that? Oh, Zorak doesn't like antibacterial agents. So the problem with this is that you can't really set a test for it, and whether or not you believe that in the Zorak one, or you believe in the properties of the Manuka honey, kind of just depends on the way that you're going to see the world. Okay. Questions about that? All right. Okay, so it does lead this question now about, so where do research ideas come from? Right? Because at this point, we've kind of talked about that as if kind of in general, you've got this type of way of that you view the world, and you might have a theory or whatever, but how does that translate into actually coming up with a research question? Okay. So the basic pattern, the basic idea behind developing a research question is that you identify, some type of association between different variables. So you're saying that this factor is related to that factor. And that relationship that you're going to identify you're trying to identify a causal relationship. So that change in this factor causes a change in that factor. So for example, let's say that you think violence on TV causes violence behavior in children. So what you're saying in this case is that here's one factor, violence on TV, and it's going to cause a change in the second factor, namely the amount of violent behavior by children. Smoking on TV, more teen smoking. Gender watcher, body image, fast food commercial, eating, etc. So you can come up with these relationships where you think that change in this thing changes that. Now, one of these is the independent variable, and one of these is the dependent variable. So which is the independent, which is the dependent? Now, the dependent typically means the thing that is being changed, and the independent means the thing that is causing the change. So is factor one the independent variable or the dependent variable? I'm going to say independent versus dependent. Independent. It's the independent variable, right? Because this is the thing that's causing the change. Factor two then is the dependent variable. It's the thing that's changing. So whenever I know it might sound a bit trite, but when you actually look at these papers, oftentimes it's really hard to figure out what the independent and the dependent variables are. So if you go back to look at this paper here,